to the next lecture of the series of modeling and analysis of DC-DC converters. So we are going through. So we are seeing the isolated DC-DC converters, the analysis and the working of the circuit and the steady-state operation of the isolated converters. We are done with the forward converter, push-pull converter, flyback converter, and now we'll see the next types of converters, that is the half bridge converter and the full bridge converter. So I'll draw the circuit diagram of the half bridge as well as the full bridge converter. So the secondary is same for both the half bridge as well as the full bridge configuration. The secondary side of the circuit is similar. So first I will draw the half bridge converter. So here is the input voltage supply V in. This is the input current I in. Then at the input side we have two capacitors. This is the midpoint of these capacitors. These have the value C. So this is V in by 2 and V in by 2. Voltage is dropped across these two capacitors. There is equal voltage sharing. Then we have these two switches. This is S1 and this is S2. Then we have these 2 points. Say this is point A and this is point B. So A goes here and B goes here. This is the primary side and this is the secondary side, NP, NS. So here I'll write the secondary side. So secondary side can be either center tapped configuration, or it can be full diode bridge configuration. So just like in the case of push-pull converter, we saw at the secondary side can have either 2 diodes with the center tap transformer secondary winding, or it can have 4 diodes, which is a full bridge diode rectifier with a single secondary winding, no center tap winding. So this is a half bridge converter, and the full bridge converter is like this. In the full bridge converter, we replace these two capacitors with another set of switches. So we have 4 switches. V in, I in, so we have S1, S2, S3 and S4. This is the point A, point B, NS, and here we have the secondary side, which is again center tap or full diode bridge rectifier. So I'll draw the secondary side. The secondary side of both the half and the full bridge is, so this is the secondary winding NS, and we have these 2 diodes. This is center tapped configuration, where these are diodes D1, D2, inductance cell C, say it is C2, and this is R. So this is I load, this is IC, and this is IL. Then we can draw ID1, ID2. Similarly, the secondary can be a full bridge configuration. With no center tap. So it is like this. This is I load, C, IC, this is D1, D2, D3, and D4, and this is connected in this sense. This is point C, this is point D, this is NS, and this is the dot configuration. So this is called as full bridge diode configuration. So in the full bridge diode configuration, we can see that in the secondary side, in the full bridge diode configuration, there are diodes. So the power can flow only in one direction, from the primary to the load, or the secondary, means from the secondary winding towards the load. It can flow in the it cannot flow in the bidirectional sense. So it's a unidirectional isolated DC-DC half bridge or full bridge converter. So in case we want to have bidirectional power transfer, we have to replace these diodes, 4 diodes, with 4 switches. So in full bridge configuration, if the diodes are replaced with switches in a full bridge, okay, I have already written full bridge, then it is called as a dual active bridge. Or DAB converter. So in a full bridge configuration, where the input side has having 4 switches, if in the secondary side, if in the secondary full bridge configuration, full bridge diode configuration, if we replace the diodes with the switches, then we have total 8 switches. In that case, that DC-DC converter is called as bidirectional dual active bridge converter. Active means there is a switch component present here instead of just the diodes. So the motivation to go from, so again in the last lecture we saw the flyback converter configuration. So flyback converter is a buck boost derived converter, and half bridge and full bridge converters are again buck derived converters. So out of all the converters, isolated DC-DC converters which we discussed till now, only flyback converter is a buck boost derived converter. Rest all, which is forward converter, push pull converter, half bridge and full bridge converter, or dual active bridge converter, all are buck derived DC-DC converters. Means the relation between output and input steady state relation is D times NS by NP into Vin. The DC transfer function is D into NS by NP, and the value of D max was 0.5. So you can select the rating of the secondary based on the turns ratio also. But it is a buck derived converter. Only only flyback converter is a push pull derived converter. And flyback converter out of the isolated DC-DC converters works on the principle of the coupled inductor rather than a transformer. Coupled inductor means that in this case we give the provision for the core. So basically the core, in this case the energy is stored in the magnetizing core. So when the switch is on, the coupled inductors are powered. One of the terminal of the coupled inductor is powered, and when the switch is off, there is no provision for the magnetizing current to discharge in the primary side. So what happens is its component IM goes to the secondary side, and thus the IM provides power to the load, just like a buck boost converter. In a buck boost converter, if we see, if we see here, this is the inductor. When the switch S1 is on, then the inductor is powered to the Vin. Similarly, in flyback converter, if the S1 is on, LM is powered to the Vin, and the load is disconnected because the diode D1 is reverse bias. Similarly, this diode D1 is reverse bias, and when the switch is off, the what happens is this inductor current gets needs a part to continue its current. So the diode D1 is forward biased. Here also in this case, what happens is the magnetizing component is appeared in the secondary like this. IM dash is appeared here, and IM dash is the current which is nothing but a part of load current. Out of IM dash, the ripple goes in the capacitor here, and the DC component goes in the load. So in flyback converter, the magnetizing current is the load current when the switch is off. So the principle is very similar. It is based on the coupled inductor and resetting the core, where the load current is where the magnetizing current is the load current, and it is based on the coupled inductor thing. But half bridge and full bridge direct DC-DC converters are isolated DC-DC converters where we incorporate the transformer, high frequency DC-DC transformer, so high frequency transformer, as an integral part of the DC-DC converter. So half bridge and full bridge converters are also very much similar to the isolated DC-DC converters like forward converter and push-pull converter. So thus, while comparing on to see why there is a need to go for half bridge and full bridge converters, we compare it with the forward and push-pull converter. We saw in the forward converter that in the BH curve, it covers only one quadrant. So working in one quadrant means the core is underutilized. The magnetic core is underutilized. So then we went for push-pull converter. In the push-pull converter, the two quadrants of BH curves are used. That is the first quadrant and the third quadrant. That is the magnetizing current becomes positive as well as negative. Then the problem in push-pull converter was that there are two switches. When one switch is on, the voltage drop across the other switch is 2 into V in. And at the secondary side, if one diode is on, for the reverse bias diode, the voltage seen by the diode is 2 into NS by NP into V in. So unlike push-pull converter, the switch in this half bridge and full bridge configuration, the voltage drop across any switch or any diode when it is off is limited to V in only. That is the advantage of half bridge and full bridge converters over push-pull converter, and thus one of the motivations to go for these converters from push-pull converter. So what happens is in half bridge converter we use two capacitors. Each of the capacitor, so based on this, each of the capacitor will be should be charged till V in by 2. Now these capacitances may be unequal. They might not have exactly the same capacitances, or they might have different values. So thus what happens is that the voltages drop across each of these capacitors may not be uniform. So there are techniques for capacitor charge balancing, where we can use any circuit components like resistors across this capacitor to maintain V by 2, or we can work in the control technique while controlling this half bridge converter, such that when the switch is on, there is an imbalance in the capacitance voltage, and for the next switching cycle, that is when switch is off, the voltage imbalance takes care of itself. That is, at the end of each switching cycle, the voltage rises and falls. There is an imbalance in the positive switching and thus in the negative switching. That is when switch is off, it takes care of the overall compensation. That is, at the end of the cycle, the average value of the voltage drop across each of the capacitors is balanced, and it is maintained at V in by 2. So what happens here is that one motivation to go for push-pull to half bridge or full bridge is that whenever a switch or a diode is in reverse bias or it is off, the voltage drop across it is never more than V in, or NP by NS, NS by NP into V in. So the rating of the device, the steady state rating of the devices are directly halved. So in a half bridge configuration, we have the two capacitor RG split output configuration, which generate V in by 2, V in by 2, which are charged up to this half of the input voltage. So these act as a two virtual or separate DC sources seen from the input side. So these are two voltage sources derived from the main voltage input source, that is V in. So here the midpoint of the AC source, this A is called as the AC point. A is called as the AC point because the potential of the node A with respect to any term. So basically based on the switching configuration, say when S1 is on, so S1 S2 operates in the complementary fashion for a half bridge. Similarly for full bridge, S3 S4 is complementary and S1 S2 is complementary. So when S1 is on, S2 has to be off. When S1 is on, primary voltage is V in by 2, and when S2 is on, primary voltage is minus V in by 2. So no, when S1 is on, the voltage across the winding is minus V in by 2, and when S2 is on, the voltage across it is plus V in by 2. Similarly, we cannot have a zero voltage switch. We here in half bridge side we cannot have a combination of the switching to generate a zero input voltage across the primary winding. But in a full bridge, what happens is when S3 and S2 are on simultaneously, diagonal switches, then in that case the VP, here it is VP, I'll write here VP, and this is VS, where this is plus minus, this is the notation, plus and minus. So in full bridge configuration, VP, when S2 and S3 are on simultaneously, it becomes V in. When S1 and S4 are on simultaneously, it becomes minus V in, and it becomes 0 when either S1 S3 is on simultaneously or S2 S4 is on simultaneously. So the voltage of, so in this case the VP voltage is of this polarity. So this becomes V in by 2 and this becomes minus V in by 2. In this case, what happens is that we have three possibilities: plus, minus, V in, and 0. So in order to have a equal distribution of the waveform, or for the symmetry, what we'll do is we'll split this voltage like this. This is one switching period. So in this case, this is V in, this is 0, and this is minus V in, and this is again 0. Or what I can directly write like this. This is 0. This is the VP waveform. This is the VP waveform. So here we can see that here it is 3 level. It has 3 levels: V in, 0, and minus V in. And in half bridge it has only 2 levels: plus, minus, V in by 2. So that is the difference. So that's why the node A is called as the AC node, because the voltage in across the primary is a AC waveform. So in the half bridge, the two devices S1 and S2 are operated in the with the same duty ratio and phase shifted by 180 degree. And the reason is because to achieve the volt second balance for the magnetizing inductance, so here it has a magnetizing branch like this, and it has its own secondary derived component. So basically, if this is the secondary leaving the dot, so here it enters the dot, so I2 or IS dash, this is IS, and this is IM, and this is I primary. Yes, this is the I primary. Similarly, that is the case. So a volt second balance is achieved. So in order to have symmetry in input output voltage side waveforms in operation, this should be the switching sequence. So that's, and for half bridge as well as full bridge configuration, the maximum value of duty ratio, so D max is equals to 0.5, which is same as the push-pull converter. So in half bridge configuration, by operating the devices S1 S2, we can get only plus minus V in by 2 on the transformer primary voltage. In full bridge configuration, we can get plus minus V in and 0. So we'll see the waveforms of the this converter of half bridge as well as the full bridge converter. We'll first see the advantages of the half bridge and the full bridge converter. So they have mostly the same advantages, that is it operates in two quadrant just like push pull converter. Then unlike the push pull converter, the voltage drop across the switches are limited to V in instead of 2 V in for primary side, and for secondary side they are limited to NS by NP into V in instead of 2 into NS by NP into V in, which is unlike the push pull converter. Then the number of devices used in the full bridge configuration is 4 in the secondary side. Yeah, 4 switches are used. Sorry, in the primary side 4 switches are used. So what happens is, if you have this 4 switches configuration, so they do not show ground for the driving circuit. So basically we have 4 switches. So this switch S3, S1 and S3 are called as the high side MOSFET or the high side devices, because say this is gate terminal, this is drain, this is source. Again, this is gate terminal, this is drain, this is source. So in this case drain is connected to line, and in this case source is connected to the, this is the ground 1 and this is the ground 2, G1 and G2. So there are 2 legs. This is leg 1 and this is leg 2. In each leg there are 2 switches which operate in complementary fashion. So for each of the switches we need gate driver circuit. So we need a high side and a low side gate driver circuit. So what happens is, they do not show the ground for driving the circuit return path. So that's why the full bridge configuration is used for power rating more than 2 kilowatt. It can go up to 100 or 200 kilowatt also for electric vehicle charging station. So half bridge configuration uses only 2 switches because it has only 1 leg. So, but in that case, the driver return path is shared by both the devices. That is, the emitter and source pins are not connected. So it increases the drive circuit capacity. Also, if you see that in half bridge converter, the voltages are of plus minus V in by 2 types. So compared to a full bridge, a half bridge primary can carry more current, which is very evident from the transformers flux balance principle. That is, V1 by V2 is N1 by N2, it is I2 by I1. So a half bridge converter is generally used for, in AC rectified output, where the capacitor bank is inherently used for filtering of the rectified voltage. That is the advantage of half bridge configuration. Then the flux walking capacitor should be used in all of the configuration, which is push pull, half bridge and full bridge. If in our control technique we do not take care of the flux walking phenomenon. So in case our control technique is very simple and it does not account for flux walking, we have to have a separate flux walking capacitor for those cases. So this was the case. So if we just see the waveform of this DC-DC converter. So now in this case it is not a couple inductor thing, so we have to denote all the current in terms of the known currents, that is the inductor current or the load current, that is the secondary side current. We have to rate it to secondary side current. So in order to do the steady state analysis, the steady state analysis means the secondary side is very similar to a push pull converter, let it be center tap or let it be full bridge diode. So the waveform of the secondary side will be very similar to push pull converter. So I will not be drawing the waveforms of the push pull converter, the steady state waveform, the steady state waveforms of the half bridge as well as the full bridge configuration again. So the secondary type waveform will be mostly similar to them. So if we draw the input or the primary side waveforms for the converter, it will be like this. First we'll draw the switching. So in half bridge thing we have two switches, S1 and S2, which operate in the complementary fashion. So as we have two switches, we have only two type of switching. So this is S1 and this is S2. So this is called as 180-degree mode of conduction. 180-degree mode of conduction means each switch conducts for maximum of this time period. So we can say that this time is T switching and this is D into T switching. This is 1 minus D into T switching. And this is, here it is T switching by 2. This is T switching by 2. So after drawing this waveform, we'll go to the switches side. When S1 is on, voltage across it is 0 and the current through it is, we'll assume that it is this configuration. Assume that it is center tapped secondary configuration. Center tap secondary configuration. So what happens when the switch S1 is on and S2 is off? The voltage across the primary is Vp. So the secondary side is like this. So the voltage across this, as per the polarity, this is Vs. This is we'll call it 3. This is, we call it winding number 4. So Vs3 will be V primary into Ns by Np. This will be equals to Vs4. So it will be positive, means the dot is at the positive. So D1 will be forward bias. So ID1 will be IL. So in that case, the voltage across the switches, for if S1 is on, it will be 0. So 0, and then when it is off it is V in. Sorry, it is V in, then it is on, Vs1, then Vs2 will be the reverse. This is V in and this is 0. Similarly, this is 0 and this is V in. These are the voltage across the devices. So we'll draw the inductor current then, because that is a known quantity. So IL will be like this. When the switch is on, so the current will be rising, then it will be falling. This is IL. Okay, this is IL and this has its average value, capital IL. Then we'll draw VL, the voltage drop across the inductor. So when D1 is forward bias, the voltage drop across it will be V in by 2 into Ns by Np minus V naught. This is V naught, so means it is positive. And when it is off, the voltage drop across the inductor will be, so this is forward bias, so it will be minus of that value, minus V naught, which is a negative value. So in this case it is this plus, and then it is minus, then again plus, then again minus. This is VL. This value is what? When S2 is on, I think I made a mistake. So instead of this S1, S2, let me call this as S2 and this as S1. Let me call this as S2 and this is S1. So my thing is that, my convention is that when S1 is on, Vp is plus P in by 2. Yes, and when S2 is on, V in is negative of Np by 2. So when it is negative, a negative voltage is induced across it. So the dot is connected at the negative. So D2 will be forward biased. So in that case, voltage across this will be, dot will be negative and it will be positive. So voltage across the inductor in one in the other cycle will be N. This will be Ns by Np into V in by 2 minus V naught, and in this case it will be minus V naught, just like the push pull thing. So this is A1 and this is A2. We can apply the volt second balance and verify the steady state relation between input and output voltage. Actually, the input side is not center tap. The secondary side is the, after transfer, the center tap one. So what happens is this voltage drop, voltage which is induced, if it was this, so this will be out of Ns, it will be Ns by 2. So, and the voltage across primary is what? V in Ns by Np into V in by 2. So it will be V in by 4. So this becomes V in by 4. Okay. So volt second balance, if we do, it will be ns by np v in by 4 minus v naught into d into t switching will be equals to v naught into 1 minus t into t switching. So it will be ns by np v in by 4 will be equals to d into v naught plus 1 minus d v naught. So d and 1 minus d will get cancelled. It will be v naught. So this is the yeah, there will be a d also. D. Because here it was these terms are ns by 2 and here these terms are ns by 2. So v3 equals vs3 equals to vs4 equals to vp into ns by 2 divided by np, and vp or v primary is v in by 2, so it will be 4. So this is the relation. So if we compare with respect to push pull, what we get is that v naught is ns by np into d effective into v in. So in this case d effective is d by 2 actually, because here in push pull it was v in. In this case it can go up to v in by 2 and v in by 2. So defective is overall d by 2, and here in this case there is no limit on d max, because d max can be 1 in this case. Why? Because there is no zero switching scale, because there are only 2 switches which operates in the complementary fashion. So there is no limit on d max for half bridge converter. So it is v naught is v in by 4 into d into ns by np. This is the steady state relation. So output side again, if we complete the output side relation, if this is the inductor current, out of it the ripple goes here to the capacitor current. This is IC, and I'll now draw the VC. IC is C dV by dt, so VC is 1 by C integral I dt. Integral of a rising edge is a polynomial facing upwards like this. It will be like somewhat like this. Then this will be a falling edge. Then again rising edge, falling edge. This is V naught. This is IC. This is A3, this is A4. This is for amp second balance. So I think output side is done, everything is done. Diode also, like, yeah, we can I think diodes are remaining, so we'll just quickly draw the diode waveforms in a single thing. So when the switch is on, diode D1 is on, and its current is ID1 is IL. And in the other case it is 0. It will be like this. This is I capital D1, and similarly we can draw I D2. This is I capital D2. Similarly we can draw voltage of VD1. VD1 when it is on, it is 0 voltage. VD1 is 0 voltage, and in the other case it is when D2 is on, the voltage drop across this will be what, minus of, yeah, V in into NS by 2 into NP. So it will be like this. This is 0. This value is minus NS by 4 NP into V in. This waveform is VD1. For VD2, it is like this. When it will be the reverse thing. This is VD2. Again, this is the same value, and this is 0 here. So secondary side, all the things are done. Then switches are remaining from the primary side. When switch S1 is on, the voltage, the current through it is I primary. Now we have to represent this current I in. So basically I in is this. I in we don't know. We have to represent this current in terms of the magnetizing branch. So the magnetizing branch for half bridge will be magnetizing branch for half bridge converter will be first for center tap, for center tap thing. So primary is this thing. So I'll draw the LM here. This is LM, then this is the transformer, and here we have center tap secondaries like this. So here what happens is, say this is winding number 1, this is 2, and this is 3. So say this is I2 and this is I3. So these currents will be I2 dash plus I3 dash. Or let's say that we change the notation of I3. Instead of this, if we draw this as I3, so in that case I3 should enter the dot like this. See, I3 is going here, then this should be I2. If I3 is coming like this, then this also should be I3. So this is I2 plus I3. So here I2 dash plus I2 dash is shown here. This is IM and this is I primary. Just before the transformer thing. So here we can write IP as the, for half bridge it is the, this current is the IP current. Also here it is the IP current. So IP current is the current. So now as we have a capacitor branches, forget about the voltage V in here. Now so assume that we have two voltages, V in by 2, V in by 2, two voltage sources. So the current from the voltage source via the switch going to the primary of the transformer, it goes one at a time, once in switch S1 and once in switch S2. So our aim is to draw the currents, these currents IS2 and IS1, IS2 and IS1, and this is IP. So once IS2 equals to IP, and in the other case IS2 is IS1. So that's why our aim is to find this. That's why we have drawn the magnetizing branch. So here what we can write as IP is Im plus I3 dash. So basically I2 plus I3. As we have a equal this thing turns ratio, as it is a secondary center tap transformer, so it will be into ns by np. Ns is ns by 2, so it will be like this. If we transfer a voltage from primary to secondary, so voltage across secondary is ns by np. If we transfer the current to primary, then it will be ns by 2 divided by np, because each of them is ns. So I2 dash is I2 into ns by 2 np, and I3 dash is I3 into ns by 2 np. So I have taken ns by 2 np as common. This is the IP current. So IP, what you can write it as D into IS1 plus 1 minus D into IS2, because when the switch is on, IP is IS1. When the switch is off, IP equals to IS2. Simply I can write in terms of this. So this is the case. So what is the value of I2, I3? We have to write. So I2 is what? I2 is the current through the I2 is ID1. I2 equals to ID1, and I3 equals to ID2, isn't it? So when switch S1 is on, ID1 is IL. I2 is ID1. ID1 is IL. IL when the switch is on, that is S1 is on, and it is 0 when off. What is off? S1 is off. Similarly, I3 is the reverse thing, when S1 is on, and here it is when S1 is off. So simply we can draw, or we can write IP as Im. Here we have to write two cases. We'll write IP as IS1 when S1 is on, and this is equals to IS2 when S1 is on, off. So this is equals to IP on, this is equals to IP off. What is IP on? IP on is Im plus IS2 on plus IS3 on. IS2 on is IL plus 0, so it is ns by 2 np, and IP off will be Im plus I2 off plus I3 off into ns by 2 np. What is I2 off? 0. I3 off is IL, so IL into ns by 2 np. So which is same, which means that the same current is passing through it. That is equals to IS1, and this is equals to IS2. So our analysis is done. We have represented the switch current in terms of the known currents, that is the magnetizing branch current and the IL current. So first we have to plot the magnetizing current. When the switch S1 is on, what happens is the core is magnetized because the positive voltage is applied to it, and when the switch S2 is on, the core is demagnetized. So I can draw like this. I'll draw Im. Then it will fall, and we are getting all the benefits of a push-pull converter. This is Im. We are getting the benefits of push-pull converter, that is, it operates in the two quadrants of operation. That is, when a switch S1 is on, the voltage positive voltage Vin by 2 is applied across primary, which means that the flux builds up in the one direction, positive direction. That is, the current Im increases linearly. The slope is given by Vm by Lm. Vm is Vin by 2 Lm. When the switch S2 is on, when S1 is off, what happens is the current starts falling because the negative voltage is applied. This negative voltage results in decrease of IL in one direction, and it may result in the building of IL in other direction. So that's why it's of twice the polarity. So this is IM. Now we can easily draw IS1 and IS2. First is IS1. So IS1 is IM plus IL. So it is like this slope or this slope. This is somewhat like this I'll draw, where this slope is IM plus IL into N S by 2 N P, and in the other case it is 0. This is IS1. Now IS2 will be what? The same when it is off. So basically here we have to write IL on and here IL off. That's why it is like this. Even this is equals to this. So these are the currents. So basically IL1 is splitted into when switch S1 is on, the current IL, so the current in the IS1 switch is IM plus IL into NS by 2 NP when it is on. When it is off, it is again the same value, but that IL is IL off. So means you can write that IM plus IL means some waveform is added to IL, that is IM, and it is just the on time period of waveform which is observed in the primary circuit. So in this case the IM doesn't has any flat top waveform, it is just a triangular waveform with 0 average value. This is A5 and this is A6. Because the volt-second balance is equals to the flux balance. Means in one time the inductor is magnetized, in the other time it is demagnetized. Similarly, A3 equals to A4 and A1 equals to A2. A1 equals to A2 we already did for deriving the volt-second balance. Now the last waveform belongs to the voltage across the switches. VS1, when switch is S1 is on, VS1 is 0, and when it is off, it is minus Vin. 0 minus Vin. This is VS1. We have done the diode voltages also, VD1, VD2, ID1, ID2. So now we have done IS1, IS2. Now with IM and IL, now we'll draw VS1 and VS2. Zero and minus Vin. So now we have drawn all the waveforms of the half-bridge converter. When we saw that using the volt-second balance, the half-bridge converter using a push-pull configuration. So even if the second is a push-pull configuration, not push-pull, even if it is a center type or a full-bridge diode configuration, the volt-second balance will still be held. The only change is in the secondary circuit. The waveform also will look mostly similar, just one or two waveform will change, that is ID1 and ID2. But the DC transfer function of V0 and Vin will be the same. And the primary waveforms also, primary side waveforms of the transformer will be the same for a half-bridge converter. Let the secondary be center type or let it be full diode bridge. So now we are done with the analysis of the half-bridge DC converter. we will quickly see the steady state waveforms of the full bridge converter, and then we'll stop the analysis with the DC-DC isolated converters. So now we'll see full bridge converter steady state analysis. Here the secondary side is a push-pull, or if we have considered push-pull, sorry, not push-pull, why I'm saying push-pull, it is the center tap. Now instead of center tap, let's consider the diode bridge, okay, the full bridge, where secondary is a diode full bridge configuration. So it will be like this. So it will be like this. This is V in, say that this is S1, I change the nomenclature, this is S3, this is S4, this is A, and this is B. Sorry. This is Vp plus minus, and this is Ip. We'll also draw the magnetizing branch. Then here we have secondary, single secondary, then a diode bridge, diode full bridge, this is R and this is I load, this is V0 plus minus, this is C, this is IC, this is L, this is IL, this is VL plus minus, and this point is connected here and this point is connected here, C, D. This is D1, this is D2, this is D3, and this is D4. So, and this is Vs plus minus, and this is Is. This is the nomenclature of the circuit. This is the circuit, full bridge converter with a secondary full bridge diode. So the secondary side is the full bridge rectifier. In this case we have 4 switches, and 4 switches are 2 legs. In one leg 2 switches can't be turned on simultaneously. So if we have 4 switches and if we have 2 switching state for each state, so we'll have total 4 to the power 2. So number of switches to the power of switching states means one switch can be on or off, it can't be other than 1 or 0. So there are 4 switches, so there can be 4 to the power 2 different switching combinations. So out of this, actually many of them will be deleted. So out of this, what happens is, okay, so let us not discuss this thing, the switching states and all. So here we have 3 switching states. Diagonal S1 S4 is on, S2 S3 is on, means 4. S1 S3 is on simultaneously, or S2 S4 is on simultaneously. And okay, I'll draw the magnetizing branch. Magnetizing branch. So it is a simple magnetizing branch. LM So it will be like this. This is IS VS plus minus VP plus minus this is IP. As it is going out of the dot, here it will enter the dot. So this is IS dash. So IP is IM plus IS dash. That is simply IM plus IS into NS by NP. This is IP. This is the relation, basic simple relation which we'll be using. And in this case, what is IS dash? Sorry, what is IS? This is IS. So the possibility for IS is to enter this diode D1, to enter this circuit D1, and again come back. So it will come back from this node, D node. So the diode will allow current only in one direction. So this you can, and also here this is IS. So this has to be IS. So it is like this in one for positive direction. So it is written from this branch. This is IS on. This is IS on. Say that when S1 S4 is on, VP becomes plus Vin. So VS becomes plus Vin. So the current IS is positive. So it will go through the point C, go to the diode D1. In that case, as positive, this dot is connected here and positive is here. So diode D1 is forward bias and diode D4 is reverse bias. And D3 becomes reverse bias and D2 becomes forward bias due to the voltage induced across the secondary. So there is only one possibility for current to flow. So when the switch S1, S4 is on, in that case, the current flows through this thing to diode D1. So IS on equals to L, but flows through D1 and D4. When it is the negative case, that is when S2, S3 is on, VP becomes minus Vin. So the magnetizing current starts to fall. It starts to fall. So VS is the negative induced voltage. In that case, D2, D3 is turned on. So D2 and D3 is turned on. So this will be IL. In that case, IL will be this. So in that case, IS will reverse its direction and it will flow like this. It will be like this. IS off. It will enter D3 and it will again, this is IS off. And IS will be always equals to IL. So the current IS splits into IS on through D1 and D4 when the switch S1, S4 is on. Similarly, the current IL splits into the diode D3 and D2 diodes, which is IS off, when S3, S2 is off. Then there is one more case, that is when voltage across the primary is zero voltage is induced, which means that there is no change in the flux in the primary side, which means that the IM or the phi M is constant, just like a push-pull converter. In that case, what happens is no voltage is induced, so no current should flow through the diode, but the inductor current should be continuous. So this inductor current will force this is leg 3, this is leg 4. This is the diode leg 3, diode leg 4, not the switching leg. So this inductor current will force either the diode leg 3 to turn on, means this IL will be equals to, so in that case D2 and D1 will be turned on and the IL will flow through capacitor, the inductor current will flow through this leg to complete its path, or it will flow through D3, D4. Or it may happen that all the 4 diodes are turned on and the current IL is split as IL by 2, IL by 2 flowing through the diode legs. This can also happen. So this is the possibility of the circuit. Now we'll quickly draw the waveforms. So yes, what we'll do is we'll see the symmetry of the IM current. So IM will increase, it will be constant, it will fall, again constant, and it will be like this. So the IM will rise only when positive voltage applied across the primary. So which means that S1, S4 is on. It will be constant if, so here there are two instances of constant. So and there are two possibilities for VP to be 0. That is either S1, S3 or S2, S4, which can interchange also, and then it will fall when S2, S3 are turned on. Then again it will, sorry, yes, this is not the case. Yeah, S2, S3 is turned on. So in this way we should split the switching of the switches. So first we'll say that this is on. Okay. So at a time, at least two switches should be turned on simultaneously. So the switching pattern should be like that. So this will be S1. We'll assume that there is a 180-degree conduction mode in each of the leg. That is when S1 is on, S2 is on. There is no dead time given. So it will be like this. S1, 1, 0, and S2 will be like this. S2, 1, 0. So this is T switching. So here there is no need to draw the T switching by 2, because here we are not seeing that the duty ratio for each of the switch is maximum of half. So that's why even here in the half bridge converter we have drawn this T switching by 2, but there was no need to draw and analyze it. So that's why we will not draw it again. This is T switching and this is D into T switching, and this is 1 minus D into T switching. We'll assume that the duty ratio for the leg 1 and leg 2 are same for the full bridge converter, and it is just phase shifted because we want to analyze this type of switching. First S1, S4 should be on, then S1, S3 should be on, then S2, S3, then S2, S4. Okay, so first S1, S4. So say that we delay the switching of S3 with respect to S1 with some time. So okay, I think there is a need to draw T switching by 2. Because we are doing the unipolar PWM technique, not the bipolar one. So for half bridge actually there was no need to draw the T switching by 2, but here there is a need to draw. So this is T switching by 2. Similarly here. This is T switching by 2. This is also T switching by 2 drawn here. So we'll delay the switching of the second leg. This is leg 1 and this is leg 2. we'll use the unipolar PWM technique. Unipolar means if there are 4 switches, what we do is the switching of the second leg is we delay the switching of the second leg with respect to the first leg by 180 degree. And bipolar PWM means that the switches are turned in the diagonal fashion. That is S1, S4 and S2, S3. There is no zero switching in it. Means S1, S3 and S2, S4 are not on simultaneously. So we can't do bipolar switching here. We can do only unipolar PWM. So in leg 1 first switch was S1. In leg 2 first switch is S3. So we'll delay the switching of S3 with respect to S1 by 180 degree, or you can say with by T switching by 2. The same waveform we'll draw here, just a phase shift is there. So this is S1 waveform and it will be like this. It will be like this. Similarly, from T switching, where is the T switching? Yeah, this is the T switching. It is like this. This is S3 and then here it is 0. Like this. S3. Similarly, S4 we can draw. Oh, I think I did a mistake. So we have to delay from here. This is S3 and S4 is this. S4, S4. So what happens is first S1, S4 is on, which is the case. Then S2, S4. Okay, so this then we have S2, S4, then we have S1, S3. So if we just move it down, so this is the switching pattern. Here if we bring it down, it will be like this. Yes. So here in this time from here to here S1, S4 is on. In this time S2, S4 is on. In this time S2, S3 is on, and in this time S1, S3 is on. Then again S1, S4, then again S2, S4, then again S2, S4 is done, then S2, S3 is on. Like this we will draw. So the flux waveform we can directly draw after this waveform, after the switching process. So flux waveform is when S1, S4 is on, the core magnetizes. There it is flat top, there it demagnetizes, again flat top, magnetizes. Here this waveform is not very perfect, so you can't see equal distances. So this waveform is belongs to IM or phi m, like this. So Now we'll draw the waveforms of the switches. We'll start with VS1. So whenever S1 is on, the voltage across S1 is 0. So we'll call it, just a second, we'll call this time as 1 when S1 S4 is on. We'll call it 2 when S2 S4 is on. We'll call this time 3 when S2 S3 is on, and time 4 when S1 S3 is on. So for time 1, the switch S1 is on. Then when S1 is off, and for other two times S1 is off. Then the switch S2 S3 is on. When S2 S3 is on, what happens is S2 S3 is on. Then what is the voltage across S1? So when S2 is on, the negative point comes here, and when S3 is on, a positive point comes here. So it will be, the voltage across S1 will be plus V, because S2 and S3 is on. So it will be V for time 3. And for fourth time, this is when S1 S3 is on. Oh, I did a mistake here. So when S1 S4 is on, VS1 is 0. For time 2, for time 4 again it is 0. For time 3 it is plus V, as we saw S2 S3 is on. Now when S2 S4 is on, that is when the bottom switches are on. Then the bottom switches, so what happens is, bottom switches are also negative is get connected here, and plus is already connected toward this switch here. So again it will be V. So it will be V only, like this. 1 2 3 4. Then again it will repeat. In 1 it is 0, 2 3 it is 1. This is VS1. This is V in, and this is 0. Then we'll draw VS2. For VS2, when S2 is on, we'll make it 0. We'll make this 0 immediately. S2 is on means 0, like this till here. Similarly, S2 S4 S2 S3, it is 0. Now when S1 S4 is on, S1 and S4 is on, we have to see voltage across S2. So when S1 is on, it is plus V in. So here it is plus V in. V in 0. And when S1 S3 is on, again when S1 is on, voltage across S2 is plus V in. So it is like this. VS2. For VS3, well, S2 S3 is on and S1 S3 is on, it is 0. Similarly, S2 S3, it is 0 here and here. VS3. When S1 S4 is on, now we are seeing what is equal to S3. S1 S4 is on. S4 is on means the volt is V in. Again it is V in. V in. And when S2 S4 is on, S4 is on is again V in. So like it is like this. I did a mistake. It is like this. Then again like this. To clearly differentiate between the light blue and the dark blue color. So now we'll draw VS4. VS4. Vs4 is when S4 is on, S1, S4 directly make it 0. 0, 0. Then when S3 is on, it is plus Vin. Like this. It is like this. So basically VS1, VS2, VS3, VS4 is nothing. VS2 is nothing but VS1 shifted by one time. It is like, it looks of this nature. So I should have done it separately, but okay. I think you can clearly identify the differences in these voltages. Uh, this you can see. Yeah. So now we'll draw the currents through the devices. Now this time we'll use the two separate axes. Yeah, so we saw that IP is Im plus Is into this, and we have to write like this. So Is, we have three conditions. Basically 4 conditions. Case 1, this is for case 2, this is for case 3, and this is for case 4. So when case 1 is there, positive voltage is there, D1, D4 are turned on. So in that case, Is is equals to IL. Is is equals to IL, and it transfers from D1 and D4. In second case, when it is 0, so Is is equals to again IL, but it flows through diode D1, D2. For case 3, it is again IL, but it goes from diode D to D3, and it is IL, it goes from diode D3, D4, just like the primary side. So this we do. So if you want to write the IP, similarly we have to write the IP. So IP will be for case 1, for case 2, for case 3, and for case 4. For case 1, what is IP? Case 1 is S1, S4 is on. So IP equals to IS1 equals to IS4. For case 2, it is S2, S4. Yeah. IP is IS2 equals to IS4. For case 3, it is IS2, S3. So IS2, IS3. And for case 4, it is S2, S3, then S1, S3. IS1 equals to IS3, which is a freewheeling current. So now what you can write is that for case 1, ID1 equals to ID4 equals to IL, and IS1 equals to IS4. So basically here, in this formula we can write Is equals to IL only. If you want to write the expression of primary current, what you have to write? IP is Im plus IL into NS by NP. So Is will be equals to Im plus IL into NS by NP. But this current is splitted into these 4 cases. sorry, this is IP, not IS. In the above 4 cases it is split. That is IP is Im plus IL into NS by NP. So let us draw the inductor current first. We should know the nature of the inductor current, then we'll be in the position to draw the further currents. So now we'll draw IL. So once switch S1 S4 is on, this is plus positive thing, so the voltage seen across the this you can call it as V1 dash. That is voltage just before the inductor. V1 dash will be what? Vs into Ns by Np plus Vs into Ns by Np. So the inductor current will rise. It will rise. In the other case, when it is 0 0, what happens is that it becomes 0. So the current starts to fall with some slope. So with some slope, or say we'll draw it like this, some slope. In the third case, S2 S3, P is minus Vn, so it is minus negative. So it is negative means negative is here, so this is conducting, negative is here, and positive is here, positive is here, so it is again positive. So it is the same magnitude. So again inductor current tries to rise with the same value, and in the last case again it falls, it becomes 0. So this is like this. This is IL. So this is IL. Now we are in a position to draw all the currents. So we'll draw the IS1 current. So the current in the IS is not the secondary current, IS1 is the current in the S1 switch. IS1 equals to IS4, which is IP, that is Im plus IL into Ns by Np. So we know Im and we know IL, so this basically we are adding, so it will be somewhat IS1 will be rising in this case. So IS1 will be activated only in case 1 and case 4. So it will be somewhat like this. It will be somewhat like this, and this value will be Im plus IL into Ns by Np. For case 1 and case 4 it will be there. So it will be like this. In other case it is 0. So again it is 1 2 3. So it will be activated in case 1 and 4. So this is the case. The reason why these are unequal is that this point is not coinciding with this point is that because Im is changed. Here Im is flat top, so Im this flat top plus this inductor current value, so the slope is somewhat reduced. But in this case the slope is again increasing and this slope is also increasing, so this will be equal to this. So it is like this. This is IS1 current. Then we'll draw IS2 current. IS2 current will be activated only in case 2 and case 3. So case 2. So it will be like this, will be like this. Case 2 and case 3. So this plus this, and again this plus this. So I think this is almost compensated. Like this, it will be somewhat like this. This is what Im plus IL into NS by N. Basically, we are adding the two waveforms Im and IL. So in case 2, Im is a flat top. In case and IL is falling. So it's addition of the two, which will be a slightly negative slope. In case 3, so IS2 comes up, appears in case 2 and 3 only. So in case 3, IM is also falling, negative slope, but IL is a positive slope. So I am drawing it with some positive, very small slope. This is IS2 current. So it will be like this and slightly current like this. This is IS2. Then IS3, IS4 is we'll draw IS3. IS3 will come in case 3 and 4. So we'll add Im and IL in case 3 and 4. In case 3, Im is negative slope and Im is a positive slope. So it will be slightly positive slope like this. And in the fourth case, Im is flat top and IL is falling. So like this. This is IS3. And lastly IS4. IS4 appears in case 1 and 2 only. So in case 1, Im is also rising slope and Im is also rising slope, so it will be like this. In case 2, also we have to add. Case 2, Im is flat top and IL is falling, so it will be slightly negative slope. This is IS4. Now we see that in case 1, IS1 equals to IS4. Is it coming or not? Yes, it is coming. IS1 equals to IS4. In case 2, IS2 is IS4. Now IS2 is this purple and IS4 is this green. So it is almost similar. In case 3, IS2 and IS3 are similar. So the purple and blue color. Yeah, it is similar. And in case 4, 1 and 3 are similar. 1 is the red one and 3 is the blue one. It is similar. So these are the switch currents and switch voltages. In primary side, we'll see if N3 is remaining or not. Im is drawn, Vp is drawn. We'll draw Vp Vs also. So, or we can directly write here. I think you can understand it. So Vp will be for case 1, case 2, case 3, case 4. For case 1, Vp is V in 0 minus V in and 0, and Vs will be for case 1, case 2, case 3 and case 4. It is V in into Ns by Np 0 minus V in into Ns by Np and 0, like this. So you can just draw the waveform of it. Now we'll go to the secondary side. Diodes. We have to draw the diode current. Now we'll use these relations of IS. So using this relation, we can say that the diode current D1 appears only in case 1 and case 2, and that is equals to the inductor current. So we'll draw the inductor current only for time 1 and 2. That is equals to the diode current D1. That is very simplest analysis to do. So in case 1 and 2, we'll draw IL current like this. This is the IL current. 3 4 3 4 it is not there, so only 1 and 2. This is ID1. And 2 ID2 will be there only in case 2 and 3. So in case 2 and 3, we'll draw ID2. It is like this. It will be like this and like this. Two and 3. Two and 3. So this is ID2. Now ID3 will draw. ID3 comes, we have to see secondary current. ID3 comes in case 3 and 4. So draw inductor current in the case 3 and 4. So it is like this. 3 4. Rest time it is 0. This is ID3. Now ID4 happens in case 1 and 4 only. So we'll draw 1 like this. And like this. Then 1 and 4. This is ID4. So we can see that in case 1, ID1 equals to ID4, which is the case here. In case 2, what we saw is that ID1 equals to ID2, which is verified. In case 3, ID2 equals to ID3, which is verified. And in case 4, ID4 equals to ID3. Yes, it is verified in the second case. So these are the diode waveforms, diode currents in the secondary. The diode voltages also we'll quickly draw. So whenever diode is off, so diode D1 is on in case 1 and 2. So for 1 and 2, the voltage across it is 0. So 0 0. In case 1 and 2, it is 0 0. VD1. Now for case 3, D2 D3 are on. So in that case, what happens is, as D3 is on and voltage induced is negative, so basically this is at positive end, and D2 is on. So basically what happens is, the voltage here is this plus and minus across CD, which is V in into NS by NP, minus V into NS by NP. this voltage comes here. D2 D3 is on, so this minus comes here, so this minus comes here, so it is minus and this is plus, so it is V into NS by NP minus of it. For case 3, 0, this is minus V in NS by NP. In case 4, D3 D4 are on, D3 D4 are on, so voltage drop across D1 plus D2 is 0. Voltage drop across D1 and D2 is 0, and diode D1 D2 both are off, so it is difficult to determine the diode voltage in this case, in these cases, because VD1 plus VD2. So we'll assume that the diodes are made of similar this thing material, so the voltage appearing across D2 D1 D2 is 0. Basically it is short circuited. In this case there will be no voltage induced across it. So what happens is, we'll assume that this voltage continues till here, like this, VD1, then we'll draw VD2, VD2. So for case 2 and 3 it is 0, it is 0, 2, 3 it is 0. For case 1 D1 D4 it is minus this, minus V in NS by NP. In case number 4, voltage across VS2, again it is undefined, so we'll assume that it is some value, but in this case VD1 plus VD2 should be 0. So if we assume that this is continuing for diode D2, so this has to be plus, like this, and it continue, yeah, like this it continues. For 2 3 it is 0, 1. For case 1 it is this, this is plus V in NS by NP, this is minus V in NS by NP, like this is VD2. Similarly the last waveforms are for VD3 and VD4. For VD3, for case 3 and 4 it is 0. This is VD3. For case 1 it is negative. This problem arises only in case 2 and 4. Now for this voltage, let's assume that this negative is continued. This is 0 0, this is minus V in NS by NP, it is continued. Now for VD4 will be VD4, we'll see where it is on. In case 1 and 4 it should be 0, case 1 0, case 4 0, case 1 0, case 4 0, 1 and 4. In 2 it is minus of this. In case 1 and 4, yeah, D4 should be 0. In case 2, when D1 D2 is on, so in that case it should be positive, like this, to maintain this consistency, and this is like this. Case 2, case 3 it will be negative, it should be negative, and case 4 again 0. minus V in NS by NP. So this is like this. This is plus V in NS by NP. Then 1, 2, 3, 4. This is voltage across the diode VD4. So quickly we'll do the volt second balance, or we'll just draw the remaining waveforms. So remaining waveforms are similar. Remaining waveforms are waveforms of the inductor, the capacitor current and the output voltage, which is very similar to the half bridge and the push-pull converter. So that will not draw. So volt second balance is what? Have we plotted VL? I think we haven't not plotted VL, so we need VL also. Okay, so we'll draw VL quickly. VL. In case 1, when positive voltage applied here, the voltage across it is Vs into Ns by Np minus V naught. This is Vs Ns by Np minus V naught. In case 2, what happens is it is 0, so it is minus V naught. This becomes minus V naught. In case 3, it is still the positive value. Why? Because the other two diodes maintain the same polarity. And in case 4, it is again minus V naught. So it is like this, oscillating. This is waveform of VL. So this is A1. This is T switching, whole T switching. 1, 2, 3, 4. So this is A1, A2, A3, A4. So in this case, there is a trick in volt second balance. In volt second balance, summation of A, which is positive, should be summation of mod of summation A, which is negative. A is the area. So we have to add the area, that is A1 plus A3 will be equals to A2 plus A4. So what we do is A1 is what? Vs into Ns by Np minus V naught or this is T switching by 2. So instead of doing the volt second balance, or we'll do the volt second balance. Volt second balance is done for the half time period. Why? Because we can do either A1 plus A3 is A2 plus A4, or we can do A1 equals to A2. But in that case, T will be T switching by 2. That is the trick. We can do both the cases. So but for that, what happens is here, this is T1, this is T1, this is T2, this is T3, and this is T4. Now we know that T1 is D into T switching, and T2 plus T3 is 1 minus D into T switching. So T2 becomes T switching by 2 minus D into T switching. T1 is D into T switching, T2 will be T switching by 2 minus D into T switching. Then T3 becomes equals to, only this time, T3 becomes T switching by 2 minus, so if this was T switching by 2, this is T switching by 2 from here to here. So again this will become T switching by 2. So T3 will be equals to T1 and T4 will be equals to T2 due to symmetry. So in this case, even if we add the area A1 plus A3 is A2 plus A4, but A1 into T1 plus A3 into T3 equals to A2 into T2 plus A4 into T4, as T1 T2 as T1 T3 are same and T2 T4 are same, which means that the 2 will be get cancelled on both LHS and RHS. So that's why we should do only equate only one area at a time. That is either equate A1 equals to A2 or we can do A3 equals to A4. So that is do A1 equals to A2 or A2 equals to A4. But in that case, the T will be T switching by 2 because we are doing the volt-second balance or the flux balance for half of the switching period compared to the flux waveform. So here the flux waveform has a period of or the frequency of 1 by T switching. But in this case, the inductor current has a frequency of twice of F switching, or it has a time of T switching by 2. That is the trick here. So that's why we are doing the volt-second balance for half of the cycle, because this inductor voltage across the inductor, it has a period of, or it has a time period of T switching by 2, and the flux has a time period of T switching. So that is the change. So A1, if we equate, A1 is Vs into Ns by Np minus V0 into T1, that is D into T switching, capital D actually, capital D into T switching by 2, A1 into T1 plus here it is minus V0 into what is T2, yeah, it into T switching by 2 minus D into T switching. This we did. So T switching it gets cancelled. So here it becomes D by 2 into Vs Ns by Np. If we send V0 there, it will be V0 D by 2 equals to 0. So it will be plus V0 into, it will be, T switching is gone, so it will be half minus T. So which will be V0 into D by 2 plus 1 by 2 minus T. V0 into D by 2 plus V0 into half minus T. So it will be V0 into half plus D by 2, or 1 plus D by 2. So therefore D by 2 D by 2 into Vs, what is it? It is not Vs, it is V in. Vs equals to V in, sorry, my bad. So here it will become D by 2 into V in into Ns by Np will be equals to V0 into 1 plus T whole by 2. I think there is some mistake in the calculation. Or okay, to simplify, what we'll do is to simplify the analysis. What we'll do is, what was the volt-second balance? Volt-second balance was VL into TL, sigma VL into TL divided by sigma T should be 0. So it will be V1 into T1 plus V2 into T2 divided by T switching by 2 should be 0, which means that V1 T1 equals to minus V2 T2, and VL1, sorry, VLI TI VL1 VL2. So in this case VL1 was Vin into Ns by Np minus V0 into T1. T1 what is, it's not T switching by 2. That is a mistake I did. It is not T to T switching by 2. So it is into T into T switching equals to V0 into T2. T2 is T switching by 2. Oh, that is a mistake I did. Sorry, I'm very sorry. Here I did some mistake. So I'll just copy paste these terms here. It is not D by 2. D by 2 comes later. So it will be V0 into T2. It's not. This is the case. D1 is D into T switching, and T2 is V0 into, I'll take T switching common, so it will be half minus T. I think now it is correct. So T switching is cancelled. So LHS is V into Ns by Np becomes equals to into D becomes equals to V0. If you take V0 common, it will be D plus half minus T. So it will be V0 by 2. Therefore V0 becomes what? 2D into Ns by Np into Vin. So for push pull, V0 is D into Ns by Np into Vin. So here in this case D effective equals to 2D. So this we can represent it by D effective for the comparison. In this case D effective equals to D. And in half bridge condition, in half bridge, what was the voltage ratio for half bridge? What was V0? What was V0? It was V0 is D by 4. I think there is some mistake here. Here it should be 2 only, not V by 4. It should be 2. Because here VL, we are using the center configuration. When the switch S1 is on, plus is connected here, that D1 is forward biased, and the voltage is V in into Ns by 2, Ns divided by 2 into Np, V in into Ns by 2 Np. This is Ns by Np by 2 into V in by 2 minus V0, and T of S this thing. So in half bridge converter, it becomes V0 is equals to 2D into Ns by 2 Np, or D effective into Ns by 2 Np, where D effective equals to 2D. So instead of like getting this, and directly write D into Ns by Np into V in. So this is the relation. So for push pull and half bridge, the voltage relation is same, but for full bridge it is different. The effective is 2D as per the analysis done here. So in half bridge we'll see that when S2 is on, negative V in by 2 is applied here. So this negative voltage comes here, the dot becomes negative, and then becomes positive. So this becomes forward bias, so positive connected here. So it is still Yeah, this thing. So I think this should continue till T switching by 2. And so okay, so this was the analysis of the half bridge and full bridge converter during this thing. And the dual active bridge is the converter where the secondary side full bridge, the 4 diodes are replaced by 4 switches. So in that case, the steady state analysis will be based on the assumption. So just like in a full bridge, we have leg 1 and leg 2. We had phase shift of leg 2 of the switches S3 with respect to S1 by 180 degree and S4 with respect to S2 by 180 degree. In the dual active bridge, instead of 4 diodes, we have 4 switches. In the 4 switches, in the 2 legs of secondary side, the switching of the second leg of secondary shifted phase shifted by with respect to primary by 180 degrees, and there is also phase shift between the primary H bridge and the secondary H bridge of the dual active bridge converter. So there is a dual phase shift, that is phase shift between the legs of either primary side or secondary side, and the overall phase shift between the two H bridges, that is called as phase shift control. So using phase shift control, we can do the analysis of the dual active bridge converter. So we are done with the syllabus of analysis and steady state modeling of isolated DC-DC converters. So in the next lecture, we'll see power semiconductor devices like diodes, MOSFET, IGBTs, etc., and the selection of the devices based on our application by doing the analysis of the datasheet and the IV characteristics and uh, um, driver characteristics for a MOSFET and IGBT. Thank you.